Welcome to the final part of the space series, where I take a look at the Fermi paradox and try to answer why we don't see evidence of aliens. In part 1, I took down the biological model of hard steps, and in part 2, I took down game theory models of Grabby Aliens in the dark forest. This time though, I'm going to present my own game theory model and my own biological solution, and finally get to the bottom of where is everybody. Observe that I have nothing up my sleeves, not a single logical fallacy, no speculations about alien motivations, and watch as I conjure the answer to the Fermi paradox, from but 3 assumptions. 1. The standard model of physics is about right, meaning that undiscovered forces will interact so weakly with atoms that they won't matter much to this analysis. Number 2. Evolution is true on other planets. As a result of this, we can assume that aliens will overestimate the probability of threats. 3. Getting to space implies not being a perfectly irrational actor. Let's start. So what are the options available to a spacefaring civilization? Number 1. You could be hostile, making relativistic weapons that take down other civilizations. Number 2. You can be hostile, making berserkers. A berserker means an expanding network of self-replicating probes that attack other things. Number 3. You could be curious, making an expanding network of repeaters and routers to get scientific data back home. Number 4. You could make a stellar beacon. Number 5. You can expand by copying your civilization. Number 6. You can do nothing. So, let's examine these in more detail, shall we? Number 1. As I showed in the previous video on game theory solutions, the trigonometric precision required to actually hit a target means this is not an actual option. Number 2. Obviously, berserkers destroy all foreign entities, meaning they need to be able to recognize you as not foreign regardless of how your technology changes over time, how your genetics might be modified, or if you even move star systems. And they need to do all this without even the capacity for being updated, because that introduces potential to be hacked and turned against you. So this is also a non-option. Number 3. In addition to this network giving you an early warning on berserkers, cosmic rays, and other existential threats, by considering each node as a vertex creating a bounded polyhedra between stars, it is much easier to find rogue planets and similar oddities in this barycentric coordinate space than by looking through a telescope. Number 4. If you think about it, a stellar beacon is not a friendly signal. It is an example of aposematism. Like a poisonous frog, it's saying, look how much energy I can waste on this nonsense, and imagine how expensive fighting me would be. So this implies they must have already done option 3. Number 5. What do you mean expand? You can't communicate with your colony unless you already took option 3, and they can't send resources back to you anyway. How are you expanding in any meaningful sense? Number 6. You got killed by an existential threat because you didn't take option 3. This gets us to our first and second force moves. First, you need to build the observation network. Second, if someone else made the network, and they're making it available to you, you must use it because making your own takes millions of years, and you need the data about existential threats right now. And this is true even if you know they're using it to spy on you. But you can optionally use it as a way to mark nodes where berserkers have already been and not backtrack, making a kind of safe zone behind them. Also of note, there is no risk to making a network. If a probe showed up in our system, we wouldn't know its top speed, we wouldn't know its replication time, we wouldn't know its generation number, and given that all the stars move relative to each other, we wouldn't have even the basic data to work out where it came from. So let's examine the game theory of this. The first civilization sets the rules of the game, so let's examine their options. Number 1. They can build an open network and allow access. Number 2. They can build a private network and disallow access. Number 3. They can build a berserker network and ensure that they are alone in the galaxy. Let's examine this network in more detail before we continue. First, because updating the network means that a hack could spread from node to node through the system, their software must be immutable, meaning that if the civilization makes an open network, they cannot later defect just because they're under new management. Secondly, it needs to be able to replace nodes that get taken out by random solar flares or asteroids, replacing nodes automatically that stop signaling, meaning that it is self-repairing and will last forever, even if the first civilization went extinct after releasing the first probe. Thirdly, you cannot use it to communicate synchronously in space because of the light speed delay. So, to use it effectively, you need to be able to get old information out of any node. Fourthly, there's a problem in propagating signals between nodes. Because the signals take years to arrive, to prevent loops where nodes keep sending the same information in a circle, the nodes need to keep records of what data they've already seen and not propagate the same thing again. From this we can conclude that each node has a copy of all data in the network from its respective light cone. So we can already conclude a lot about this data network just from thinking about the physics of space. But wait a minute, did I just sneak a premise? That the nodes would all be sending information to all visible nodes instead of just the nodes on the way to the home civilization. The key insight here is that data storage nodes have no more hardware costs than the pure router nodes. They don't even have different parts, just different ratios of parts, and because of the replicators, the cost function of both is 0. So the cost is in the initial software. Meanwhile, the software for sending only back home has to keep track of all the stars relative to each other, and it has to have a solution for nodes being down. Solving this problem is far more expensive and far more likely to go wrong. The easiest solution is to just put it in the too hard pile and send everything everywhere. What kind of alien would build a public network? Well, bearing in mind they have control over what signals get propagated, what information gets shared, and can spy on the users. If they are altruistic, they will share it to help out. If they are mercantile, they will share it to trade intel. If they are paranoid, they will share it to spy on users. If they are hostile, they will share it to seed disinformation and waste time on dead-end technologies, as well as convince them that successful technologies are dead ends. So bearing this in mind, who builds a private network? None other than the apathy aliens from the apathy planet. Of course, they won't be motivated enough to do astronomy in the first place. And who is motivated to make a berserker network? The commonly cited game theory here is that it prevents someone else from using berserkers on you first. However, when berserkers encounter a network, they can either A, ignore it, in which case it will propagate back home that something is replicating and expanding influence. Number 2, they can destroy a node, in which case the signaling itself is a signal. Number 3, they can destroy it and try to copy the signals, in which case they don't have the encryption keys. No matter what they do, given their replication time, and that things in space can only move by hopping short distances from star to star, the wavefront of berserkers will probably only move at 20% light speed, meaning the civilization with a network will average several millennia of advanced warning. For example, at 1,000 light years away, you will have 5,000 years. In addition to this, it may trip built-in anti-berserker defenses that destroy it, much like white blood cells. Additionally, you can't transport resources between stars anyway, and if you could, dead civilizations' resources are no more accessible than that of uninhabited systems. So, the only motivation left is pure spite. In game theory, this fails to meet the criteria of a Nash equilibrium because there's no benefit for the civilization defecting. It provides no strategic advantage, it creates existential risks, it gives you less information now that you have no trading partners. So the game theory has reduced it to the following: build or join the public network or go extinct. Now we have to re-examine some of the available options for motivations. Number 1, altruism, share all information. Number 2, trade information for information. 3, paranoia, share no information but spy on others' information. 4, hostility, share disinformation. But if we think about it, as an altruistic alien like Kal-El, you have a problem. Freeloaders and spammers can overwhelm the system and ruin it for everyone. You need some way of moderating the value of interactions, throwing out junk and incentivizing constructive behavior, or the network loses stability. And the paranoid aliens face this same problem. So both these motivations immediately fold into the trade motivation. Furthermore, there's no risk of worrying about a technological arms race because by the time you get information, it's already thousands of years old. Now for the hostile motivation. In addition to facing the same problem, they have the additional overhead of creating realistic seeming disinformation, making sure the ratio is such that the network stays in use, they can't mislead about things that are too independently verifiable, and they risk others getting frustrated and building their own networks, in which case they lose control. Furthermore, if we examine the motivation, if I share my information, they may become a threat to me later. A threat how? The only option for offense is berserkers, and they're already swimming in your anti-berserker defense system. What's the point? Additionally, by attacking you, they risk losing network access. There's no rational motivation for this hostile approach. The only purpose, again, is pure spite. It fails to even reach the level of a Nash equilibrium. And finally, for the apathy aliens, if they want to expand later, they need the trade system so different copies of their own civilization can communicate across thousands of light years of delay. So the game theory of space is actually a single dominant strategy. First force move. You must make an observation network because there are existential threats in space. Second force move. If someone else has one, you must use it because making your own takes millions of years, and you need that data now. Number 3. The first civilization must choose a public network because private networks only serve the apathetic and hostile networks have no discernible advantage. Number 4. The network must be a self-repairing mesh network where each node has a complete copy of the data for asynchronous communication. But you may be wondering, if building the network takes billions of years, why does the first civilization do it? Why don't they just expand to maybe 10 stars out? The answer is simple. Because the nodes are self-replicating machines, and they can't really tell the difference between a star that doesn't have a node installed and one where the node broke. Replicator is going to replicate. Much like a bacteria taking over a whole pond, the replicators will eventually take over the whole galaxy. So let's consider how it works as a communication platform. Because civilizations are thousands of light years apart, diplomatic relations are meaningless. So the trade system needs to be fully automated, determining the value of data and exchanging it for equally valuable data. This sounds like it may be hard. Am I doing the same thing as Grabby Aliens where I wave the technology wand and say, well, future technology will be able to go at a significant fraction of c, even though decelerating from these speeds violates conservation of energy? No. Making this kind of network is next 100 years kind of stuff. We already have robots working in factories making themselves, and the trade system isn't even hard with current technology. We don't even need to solve the communication problem to do it. Here's an example implementation. We'll give each node a data store. In this data store, we'll mark specific to this node what is publicly available, what is privately available, and what is user submitted. The public data is just accessible. To move something from private to public, what you need to do is provide data of equal value. What we can do is train a transformer model on all the user submitted and public data. Run the model on the incoming data and get the error. This will tell us how novel the data is. We multiply the transformer error times the compressibility times the byte length. This will select things that are novel but not noise and not word salad. If you're the paranoid aliens, we can make it so the only way to determine if a document has already been submitted is to submit it and see if it has zero value or not. This will encourage the submission of classified military intel to access alien cat videos, because, it's not like anyone's going to catch you. While we're here, let's take a look at the energy requirements. For the data signal, we can use an X-ray laser. Because the spread of a laser depends on its frequency, this will have a very low spread, meaning we don't need all that much energy for it to still be detectable even several light years away, less than 1,000 watts. Now all we need is some way to actually hit the receiver. Again, we can use a laser for this. A high UV laser will give us wider but still low spread, so we can get away with only a few kilowatts of power, and this one can even pulse instead of requiring continuous power. But this leads to our next forced move. If we want to trade, the target civilization needs to actually know how to use the platform. We need to make contact. Additionally, we may need a contact system in place anyway because in event of a civilizational disaster, we may lose the API key to the network. And this leads to our final forced move. If we want to trade with the Orca people of the Orca planet or the Slug people of Mollusk 4, we can't rely on capability to build a radio. But what about the paranoid aliens? They don't care about someone using their network if they wouldn't be a potential threat anyway. It's no good to spy on them. But if they don't have a contact system, then no one knows how to use the network and they can't spy on them. They can only get unencrypted data that is being broadcast anyway. Furthermore, they can't predict who will become a threat in the future, what path the civilization might take, and if they wait to see, they'll need many more potential contact protocols, with each one being a chance for something to go wrong. This leads us to the vending machine model of first contact. You just kind of leave a vending machine on the planet and wait for something to evolve that's smart enough to figure out, if I put my arrows on this thing, it'll give me a picture of a flower, and just figure out how to use it by curiosity. The only requirement is object manipulation and ability to learn. This solution to first contact is asynchronous, sidestepping all ethical dilemmas surrounding the problem. For example, readiness. It's self-rate limiting by the value mechanism. Cultural imperialism. Things that are common to other cultures are more predictable by the transformer and of lower value. Power imbalance. It's asynchronous communication with probably extinct civilizations. Recognizing intelligence. Anything that can use the system is smart enough to engage with it. When to make contact, the species can decide for itself. That's the game theory of space. Create a communication service so that you can harvest data. The fact that we don't see any nodes that are essentially honeypots for hostile civilizations, or any kind of contact machine, is the evidence that we are actually alone. But this isn't really a solution now, is it? It answers that we are alone, but not why we are alone. Let's start by getting some recent values for the Drake equation so we can understand the scale of the problem. Rate of star formation in the galaxy is estimated at 1.5 to 3, so I'll use 3. Fraction of stars with planets, 100%. Fraction of stars that could support life, 40%. For the fraction that go on to develop life, I'll use 100%. And I'm going to change this a little bit. Instead of the fraction that develops intelligent life, I'm going to use the number of speciation events per year, 3, times the number of years that a speciation event occurs where intelligence could hypothetically develop. I'll put this at 1 billion years, times the number of these species that go on to develop rockets. Because what we should be able to detect is these probes. Radio signals turn to noise in space very quickly, so we shouldn't expect to find that. Times the length of time we expect to see signs of civilization for. I'll put this at 5 billion years because for most of the early universe there were too many gamma ray bursts for life, but we should expect the probe networks to hang around forever. So this puts us at FR times 1.8 times 10 to the 19th. Or if you prefer more computery numbers, FR times 2 to the 63.96. So the problem is, where do we get a number for FR? And why would it be so low as to explain why we don't see any evidence of aliens? This gets me to the first major misstep of models like hard steps. It views evolutionary history like a logical progression where one trait naturally leads to another, but this is the post hoc fallacy. Even when a trait would be advantageous, Bookstein's argument shows that the necessary genetic mutations to make it selectable may never arise. The developmental pathways simply might not be accessible through random mutation, no matter how useful they would be. For example, consider that if snakes got a mutation for stronger nails, it wouldn't matter that they don't actually have fingers and cannot express this gene. The mutation occurs regardless of whether it's useful or selectable. We often confuse what gets selected with what mutations are possible, thinking, of course trait B follows trait A. But the mutations for trait B happen regardless of whether trait A exists or not. The fact that nails are only useful if you have fingers doesn't make nail mutations more likely in species that have fingers. Selection pressure only works on what mutations randomly occur, and many theoretically useful traits may never get the right mutations to make them selectable at all. So what actually are the chances of getting the right traits you need to get to space? Let me use some simple probability math to illustrate just how specific this combination of traits is. While this isn't how evolution works, I'll show you why drift makes this model more applicable than you might think. Well, obviously it needs to have dexterous manipulators that aren't so dexterous that they become too computationally expensive. Let's put this at 50%. It needs to be intelligent, and bearing in mind that most of these species will be maybe plants or something, let's put this at 50%. It needs to have vision that's clear enough to actually see the stars. Based on Earth, this is about 2% of animals, which is why I'm putting this at 50%. It needs to be a tool user, it needs to have a Turing-complete language, it needs to be small enough that the square cube law doesn't preclude it from making a rocket, it needs to have a small enough hitbox that it can work in tight spaces to make machines. Humans seem to be completely unique in having this weird compulsion to kidnap animals and make them live with us. This seems like it might be necessary for domestication, and domestication was needed for early cities. So I'll add that in too. We humans don't like to admit it, but we're scavengers. Yeah, our stomach acid is in line with the vulture, and we just love food that's partially rotten. Being a scavenger is necessary to be able to preserve food for winter via fermentation. And so on in that fashion. If we can get a trait list 64 traits long, then we have 1 over 2 to the 64 times 2 to the 63.93 less than 1. And yes, we only have about 14 traits so far, but the actual probability of them per speciation event is closer to 1%. We only need 10 1% probabilities to get the same answer, or even 4,099.999% probabilities, which sounds like a fossil record. What I hope this illustrates is just how specific of a combination of traits we're looking for, and how close you can get to it without hitting the quote-unquote winning combination. For example, Neanderthals were almost completely identical to us, and they were around for twice as long, yet they never even got to cities. We can consider this necessary combination of traits as a sort of rocket building niche. And this niche is interesting because there's no conceivable environmental pressure to select for it. So how did we get into it then? Let me introduce you to the neutral theory of evolution, proposed by Moto Kimura in 1968. It holds that most evolutionary changes are caused by genetic drift, and has been extensively validated through genomic studies. This is why the null hypothesis for why an animal is a certain way should be that it's just like that for no reason. To help illustrate how this fits in to the natural selection framework, think of evolution as existing on a spectrum. On one end of the spectrum is one species linearly progressing to the next via selection pressure, and on the other end is extensive branching due to drift. Most speciation events lie in the middle of this spectrum, with things tending more towards the linear end of the spectrum when they have large breeding populations with short lifetimes, and towards the drift end when they have small breeding populations with long lifetimes. So what does human evolution look like? Well, like a branching bush, heavily dominated by drift, which is to be expected, as for most of human history, the peak population size of our ancestors was only 50 to 100,000. And when it wasn't, such as with Homo erectus, they tended to be an isolated breeding group, shouldn't be considered as a kind of large population you need to become selection dominated. Now, when we became most human typically follows extinction events where drift becomes even more dominant. For example, we got symbolic manipulation after the Toba supervolcano event that reduced us to about 1,000 individuals, well after our split from Neanderthals. Furthermore, despite all the speciation, all these hominids tended to have the same kind of small population sizes. They weren't getting any better at surviving. For example, Paranthropus boci was a hominid being selected for to eat grass, which is just not sufficient energy for a great ape. And in our own lineage, scavenging behavior started in a similar time frame. As I mentioned before, we have the stomach acid of a scavenger. Note though that neither adaptation seemed to notably increase the population size of either hominid. They were both just as bad at surviving as they were without the adaptation. This reveals a second stuck premise of most Fermi paradox solutions. They assume that humans are at the top of a crab mountain. Nature just loves making crab. This means that the evolutionary maxima that the crab lives on is very broad and easy to climb up. And most Fermi paradox solutions take for granted that humans are on top of one of these crab mountains, where fairly intelligent things with manipulators will naturally climb to the top of it. But a more appropriate animal to compare it to might be the koala, who nature doesn't love making, and like our ancestors, is just plain not that good at surviving. Because evolution isn't survival of the fittest, but rather survival of the kind of good enough. To state it bluntly, technological civilization is not an adaptation. It's what happens when a species becomes so maladapted to its own niche that it has to invent its way out of extinction. Extensive tool use was a successful adaptation because we were already failing at being animals. In other words, evolution is not failing to create technological civilizations on other worlds, as in the Great Filter or Hard Steps. Rather, it is succeeding at avoiding these fitness valleys. We're like a cosmic Timothy Dexter, the merchant who got rich by making all the wrong moves. We didn't evolve to be technological because it was the best path. We essentially failed upwards into it. But what are the odds of this happening? Prior, I said not to take my rhetorical device of independent probabilities too seriously because that's not how evolution works. Animals are not just randomly generated. But when animals fall into these extended periods of drift, which trace they had prior is essentially random because the drift is caused by environmental change, nothing about the animal. And which traits you get due to drift, as well as which traits you lose due to drift, is also random, so it does just reduce to a lottery. Even if every trait is very common, the odds of getting them all instead of just dying in the drift period are astronomically low. The fundamental paradox of the Fermi paradox is this. By trying to avoid human bias by assuming we're common, we've actually created the ultimate anthrocentric bias. We've turned our specific weird combination of traits into evolution's finish line, and that's why no one else has crossed it. Of course they haven't. Evolution doesn't have a finish line. Evolution is not a directed process, it's a random walk. An orca is brilliant at being an orca. This model also makes some interesting predictions. See, earlier I used a 100% chance for abiogenesis, which may have seemed arbitrarily generous. But actually, this solution requires it for the Copernican principle to hold. For us to win this improbable jackpot of spacefaring traits, there needed to be an enormous number of lottery tickets. We need life to emerge easily and diversify extensively to have enough species trying different combinations of traits. And that's exactly what we see in Earth's history. Life appeared relatively quickly after the planet cooled, and we see countless species that evolved some of these traits but not others. Corvids got tool use, octopi got manipulation, dolphins got intelligence. Lots of partial winners. But only one species hit the full combination.